So this is a lesson on trigonometric substitutions and integrations with trigonometric functions. And we have to remember the basic trig identity, which is for any angle theta, sine squared theta plus cosine squared theta equals 1. If we take this identity and divide by cosine squared theta, you get sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals 1 over cosine squared theta. And sine over cosine is tangent squared. Cosine over cosine is 1. And 1 over the cosine is the secant squared. So these are two fundamental trig identities which we use a lot. Now, what's an example of how we can use them? So suppose we have an integral that looks like, let's say, sine cubed x cosine to the 4th x dx. So the important thing here is that at least one of these exponents is odd. Well, 3 is odd. So let me write this like this. The integral of sine x times sine squared x times cosine to the 4th x dx. Because this is just sine cubed. This is the integral. Sine squared, I can write as 1 minus cosine squared times cosine to the 4th times sine x dx. That's the sine x dx. If I make a substitution, u equals cosine x, du is minus sine x dx. So if I substitute, I get the integral of 1 minus u squared times u to the 4th. Sine x dx is minus du. So if I just multiply through, I get minus u to the 4th plus u to the 6th, or u to the 6th minus u to the 4th du. That's easy. That's 1/7 u to the 7th plus 1/5 u to the 5th plus a constant. U is equal to the cosine. So this is 1/7 cosine of x to the 7th minus, oops, I lost the minus sign, minus 1/5 cosine x to the 5th power plus a constant. That's the solution. Let's just check. What is the derivative of 1/7 cosine to the 7th x minus 1/5 cosine to the 5th x? So derivative of 1/7 cosine to the 7th is 1/7 times 7 cosine x to the 6th times minus sine x minus 1/5 5 cosine x to the 4th times minus sine x. The 7's cancel. I get minus sine x cosine to the 6th x plus sine x cosine to the 4th x. That's equal to sine x cosine to the 4th x of 1 minus cosine squared x. This is sine squared x. So we get sine cubed x cosine to the 4th x. That's what we were supposed to get. So if we have sine to an odd power times the power of the cosine, we would pull off one factor of the sine. We're left with an even power of the cosine, which we can turn into the even power of the sine. which we could turn into the cosine. Okay, let's do a few more examples. These are fun. Suppose we have, this is example 2, the integral of cosine cubed x over the square root of the sine of x dx from pi over 6 to pi over 3. Again, the important thing is that we have the cosine to an odd power. Then we write this as the integral from pi over 6 to pi over 3 cosine squared x times cosine x dx over the square root of the sine of x. Cosine squared is 1 minus sine squared over the square root of the sine of x dx from pi over 6, pi over 3. Now, oh, times the cosine x. Forgot that, that's important. Don't forget that cosine x. Cosine squared is 1 minus sine squared cosine x dx. So now I make the substitution, u equal the sine of x. So du is cosine x dx. What I get is the integral 1 minus u squared over the square root of u du. And when x is pi over 6, the sine of pi over 6 is 1 over u3. When x is pi over 3, the sine of pi over 3, let's see, what is this? This is 1 1/2 u3 over 2. The sine of pi over 6 is a half. The sine of pi over 3 is u3 over 2. So this becomes, this is an integral from a half to u3 over 2. This is this integral. This is u to the minus a half minus u to the 3/2 du. The integral of u to the minus a half is 2u to the 1/2. The integral of u to the 3/2 is 2/5 u to the 5/2. So this is evaluated from a half to u3 over 2. So this is 2 times the square root of u3 over 2 minus, oh, let me just write it slightly differently. u3 over 2 to the 1/2 minus 2/5 u3 over 2 to the 5/2 minus 2 times the square root of a half minus 2/5 times 1/2 to the 5/2. So this is 2 u3 over 2 to the half minus 2/5 u3 over 2 to the 5/2 minus 2 over root 2 is the square root of 2. 1/2 to the 5/2 is 1/2 to the 2 plus 1/2. That's 1/4 times 1 over the square root of 2. And if we multiply that by 2/5, we get we get 2/5 times 2, 2/5 times 1/2 to the 5/2 is 1 over 4 root 2. So this number is 1 over 10 root 2. And that's what it is. Done. That's the proof. Now, in the case where you have an integral of cosine, this is the way the text does. The nth power of the sine times the nth power of the cosine, and m and n, neither of them is odd. But let's say they're both even. They don't have to be integers, but let's say they're both even integers. There are substitutions we can make to make the problem more doable. So remember, we have the identity that the cosine of 2x is cosine squared x minus sine squared x. And if we write cosine squared as 1 minus the sine squared, this is 1 minus 2 times sine squared x. So sine squared x is equal to 1 minus the cosine of 2x over 2. And if in this identity we replace the sine squared, if we say this is cosine squared x minus 1 minus cosine squared x, so we get 2 cosine squared x minus 1. We obtain cosine squared x is equal to 1 plus the cosine of 2x over 2. So when we have even powers of the sine or the cosine, we can replace them by these functions of cosine 2x. So here is an example. The integral of the 4th power of x dx. So this is like the integral of cosine squared x squared. Cosine squared x is this. The integral of 1 plus the cosine of 2x over 2 squared dx. If we expand that, we get the integral of 1 plus 2 times the cosine of 2x plus cosine squared of 2x over 4. So this is the integral of 1/4 dx plus 1/2 the integral of cosine of 2x dx, plus the fourth, the integral cosine squared of 2x dx. Again, we can use this identity, replacing x with 2x. The integral of cosine squared of 2x is equal to 1 plus the cosine of 4x over 2. Replace x by 2x, you get 1 plus cosine of 4x over 2. The integral of a half is a half x. The integral of cosine 4x is 1/4 times the sine of 4x. Take this, plug it in here. These two integrals should be easy now, and we're done. And the details you'll find in the textbook. There are also other ways to solve an integration problem. What we just did was we had trigonometric integrals, and we ended up somehow getting rid of all the trig functions. Here we can have an integral where there's no trig function, but if we introduce it, we end up with something that we can actually solve, not so without much difficulty. So again, we have to remember the basic identities, namely cosine squared x is 1 minus sine squared x. Secant squared x is 1 plus tangent squared x. And tangent squared x is secant squared x minus 1. So this is really going to allow us to make substitutions when we have something which looks more or less like 1 minus u squared, 1 plus u squared, or u squared minus 1. So these are the formulae that we want to keep in mind. So let's do some examples. It's the only way to see really what is going on. Suppose we have something which looks very hard. The integral of 1 over x squared times the square root of 9 minus x squared. So 9 minus x squared, that's something minus a square. I can think of this as dx over x squared. Factor out 9, square root of 9, you get the third square root of 1 minus x over 3 squared. Suppose I let x over 3 equal the sine of theta. It says I'm making the substitution x equal 3 sine theta, dx is 3 cosine theta d theta. So when I substitute, I get 1/3 the integral. Dx is 3 cosine theta d theta. X squared is 9 sine squared theta. Square root of 1 minus x is square root of 1 minus sine squared theta. This is equal to the cosine of theta. So it cancels that. This cancels this. So it looks like I have 1/3 the integral of 1 over sine squared theta. Right, 1/9. 1 over the sine is the cosecant squared theta. And the derivative of the cosecant squared is the minus the tangent squared. But I want to get an answer in terms of x, so how can I get from the cotangent back to x? So remember, cotangent of theta is cosine theta over sine theta. That's the square root of 1 minus sine squared theta over sine theta. Sine theta is x over 3. It's the square root of 1 minus x over 3 squared over x over 3. So this is 3 over x, the square root of 1 minus x squared over 9. Or like this is square root of 9 minus x squared over 9. Square root of 9 is a third. The third cancels at 3. It's 1 over x times the square root of 9 minus x squared. But the integral of the cosecant squared is minus the cotangent. That's the cotangent. So what we get as our answer is minus 1/9 square root of 9 minus x squared over x plus the constant. Let's try another one. This is example 2. We have the integral 1 over square root 4x squared plus 1. So remember, we have the identity tangent squared theta plus 1 equals secant squared theta. This is the integral dx over the square root of the quantity 2x squared plus 1. So I'd like to make a substitution with 2x is equal to the tangent of theta. So x is a half times the tangent of theta. The derivative of the tangent is secant squared. So if I make this substitution, this becomes the integral of, in the denominator, the square root of tangent squared theta plus 1 dx is a half secant squared theta d theta. This is 1/2 tangent squared theta plus 1 is secant squared. Square root of secant squared is secant theta. This just becomes the integral of the secant of theta d theta, and you can look it up or you can remember it. It's equal to secant theta plus log of secant theta plus tangent theta. And that's the proof. We'll do one more, example 4. This is a definite integral. The integral from the integral from the square root of 3 to 2 of the square root of x squared minus 3 over x dx. And we know that secant squared minus 1 is the tangent squared. So we would like x squared to be equal to 3 times the secant squared of theta. Because if I do that, then I would get the square root of 3 secant squared theta minus 3 over x. Well, in this case, x would be the square root of 3 times the secant of theta. And the derivative of the secant is the secant times the tangent. So when we substitute, so this is square root of x squared minus 3 over x times the square root of 3 secant theta tangent theta d theta. When x is square root of 3, secant theta is 1. 1 over the cosine is 1. Cosine of 0 is 1. When x is equal to 2, the secant is 2 over root 3. The cosine is root 3 over 2. In that case, the angle is pi over 6. You do need to know the elementary trig expressions. So what do we have here? The root 3's cancel, the secant cancels. This is equal to, I can factor out a square root of 3. The integral from 0 to pi over 6. This is the square root of secant squared theta minus 1, tangent theta d theta. Secant squared minus 1 is the tangent. So this becomes root 3, the integral of tangent squared theta d theta from 0 to pi over 6. Root 3, the integral. Tangent squared theta, it's easier if I just write this as secant squared theta minus 1. The integral of the secant squared is the tangent. The integral of 1 is theta. So it's this evaluated from 0 to pi over 6. So we get square root of 3. The tangent of pi over 6 is 1 over root 3 minus pi over 6. The tangent of 0 is 0 and theta is 0. So what we get is 1 minus root 3 pi over 6. Okay, trig substitutions, that's it.